Welcome to the webinar on modeling hyperelastic materials in COMSOL Multiphysics. My name is Chandan Kumar, and I am an applications engineer here in our Boston office. Today we'll discuss important concepts in hyperelasticity modeling, and we will show you how to set up a hyperelastic model in COMSOL. The demonstration will include modeling the compression of a spherical foam between an indenter and a rigid base. This will also involve contact modeling, but we will discuss more about this later on. First, let's discuss a bit about hyperelasticity. Hyperelastic constitutive laws model materials that respond to elastically when subjected to large strain. They are used to model both nonlinear stress-strain relationship and also large shape changes. They're used to model elastic behavior or rubber-like materials, like biological tissues and foams. The figure on the right shows a stress-strain plot for a hyperelastic material where the stress-strain curve becomes nonlinear for large strain. In addition, if the load is removed, the material will return to its unstressed state. The stress-strain relationship of a homogeneous hyperelastic material is given by specifying its strain energy density, which is a function of the deformation of the material. Stress with respect to the strain is then calculated by differentiating the strain energy density function. If we talk about a purely hyperelastic or perfectly elastic material, then in those cases, the internal dissipation associated with the mechanical process is zero. So the stress in such a material does not depend on strain rate. Now let's review some of the basics of hyperelasticity, which is important in understanding mathematical modeling of hyperelastic materials. And before I move on, I would like to encourage everyone to submit their questions via the questions window that you see here, and I will try to address them as I go on, or I'll try to address them at the end of the presentation as well. We'll have some time at the end of the presentation as well. But please do type out your questions in the questions window. Now, the first expression or equation that you see here shows the relationship between second Piola-Kirchhoff stress tensor, that is S, and the strain energy density, that is WS, where stress is given by the derivative of strain energy density with respect to the Wright-Cauchy-Green tensor, that's C. For an isotropic hyperelastic material, we can further expand the above definition of stress and write it down as a function of derivative of strain energy density with respect to invariance of the Wright-Cauchy-Green tensor. This is as per a theorem known as the representation theorem for invariance, where the strain energy density can be written in terms of strain invariance I1, I2, and I3. These strain invariants are calculated by knowing the eigenvalues of the Wright-Cauchy-Green tensor. And the Wright-Cauchy-Green tensor by itself is calculated as F transpose F, where F is the deformation gradient. Now, as we discussed, the strain invariants are functions of the eigenvalues of the Wright-Cauchy-Green tensor. This actually is derived by writing the Wright-Cauchy-Green tensor in its spectral form, the form that you see here. This is known as the spectral form. In the top equation, lambda A squared values are the eigenvalues of C, which is in turn calculated from the equation determinant of C minus lambda times identity matrix is equal to 0. The vectors NA represent the principal referential directions, which are same as the directions of principal stresses, which you may already be familiar with. While all of this mathematics is fine, one good way to interpret lambda A is to think about a uniaxial deformation, where of course the principal referential direction is along the stretching direction. So lambda A in such a case actually represents the ratio of the deformed length to the undeformed length along the stretching direction. In the case of stretching, lambda A will be greater than 1. And in the case of compression, lambda A will be less than 1. In terms of uniaxial strain, you can write lambda A as 1 plus uniaxial strain. All right, so let's see, we have a few questions here. Let's see if any of these I can answer right now, or they're relevant right now. We have a question here from Montser about, will we discuss FSI as well, meaning fluid structure interaction with hyperelasticity? Well, while we'll not discuss FSI specifically with regards to hyperelasticity, whatever we will talk about hyperelasticity applies to FSI as well, except that in FSI, you also have to worry about fluid flow calculations as well, and mesh would be an important thing as well with regards to FSI. So my only suggestion there with regards to hyperelasticity is everything that we discussed today will be a part of such a model. But as far as mesh is concerned, there you'll have to take a little bit care. And so we can talk about that mesh when I do a demonstration. We can talk about the meshing in FSI as well. Now that we know what lambda A represents, we can also rewrite our stress equation as a function of lambda A, or in other words, represent the second Piola Kirchhoff stress tensor in its spectral form, which is here. And this is important, and we'll see why it is important later, because sometimes the strain energy density of hyperelastic materials are represented as a function of these principal stretch values, that is lambda A. Now let's talk about compressibility and near incompressibility of hyperelastic materials. Now here, near incompressibility means slightly compressible. So for such materials, there is a volume change and they behave quite differently in bulk and shear modes. It is therefore beneficial to split deformation into so-called volumetric part and the isochoric part. Now the volumetric part represents volume change and the isochoric part represents volume preservation. The deformation gradient, the Wright-Cauchy-Green tensor, and the principal stretches, they're all represented using a multiplicative decomposition as is shown here, which means F, the deformation gradient, is represented as a product of the volume changing part and the volume preserving part, F bar. As a result, the determinant of F bar is 1. Same goes for the Wright-Cauchy-Green tensor and the principal stretches. The strain energy density function and the corresponding second Piola Kirchhoff stress tensor, they're all also represented as a sum of the isochoric part and the volumetric contribution, like you see in the equation here. Multiplicative decomposition, the deformation gradient, and the Wright-Cauchy-Green tensor then leads to a new expression for stress in terms of modified invariance I bar that you see here. These expressions for stress are useful in determining stress as a function of strain energy density and invariance or principal stretches for different types of hyperelastic material models. And we'll see this in a bit in a little more details, why this is important or how is this really come into play in our modeling process. Now, there are numerous specific forms of strain energy density functions in literature that describe the elastic properties of incompressible as well as compressible hyperelastic materials. And even more efficient forms are regularly published almost every month. So in terms of the hyperelastic material models in COMSOL, COMSOL has several inbuilt hyperelastic material models that you see here in the screenshot on the right-hand side, starting with Neo-Hookian, Moni-Rivlin, Ogden, Verga, Yo, Aruda Boys, Jen, Gao. These are for rubber-like materials. Then you have Storakers, Blatsko for hyperelastic foams. And in addition, you also have inbuilt hyperelastic material models. You also have the option to use user-defined hyperelasticity to model any other hyperelastic formulation that is not built in COMSOL. So the next question here is, how do we choose a particular material model? And this process involves few steps. So I want to go through the few steps that are involved in modeling hyperelasticity. Now, before that, we have a question here from Thomas. What is geometric nonlinearity in the verbal definition of elastomer shown right in the beginning of the presentation? Geometric nonlinearity is basically associated with the concept called large deformation. What it really means is, usually if you read a standard undergraduate level textbook, for example, you will see the strain definitions are linear with respect to the displacements. They are proportional to displacement gradient raised to the order 1. But that is not true in reality whenever you have large deformations, as is the case in hyperelastic materials, where you have large deformation and large strain. So in those cases, the strain definition is actually quadratic in nature. So whenever you model hyperelasticity, you have to have that definition of strain in the hyperelastic material model, and not the linear definition that you normally use for small deformation in linear elasticity. When you do modeling in COMSOL, that is automatically checked. So you automatically incorporate geometric nonlinearity, and you don't have to do anything extra to include it. All right, so the first step to modeling a hyperelastic material is to first figure out what material model are we going to use. And to figure out what material model that we will use, the first step is to conduct experiments or tests to obtain experimental data corresponding to stress versus strain, or stress versus stretch, or force versus strain, or force versus stretch. Any of these relationships that you can gather from your experimental data are useful for figuring out what hyperelastic material should you be using. Some of the common tests are listed here in the slide, and they include uniaxial tension or compression, biaxial tension, where the sample material is stretched in 2 distinct directions, a volumetric test, where a sample is subjected to hydrostatic compression in all distinct directions, or a pure shear test, where a thin sheet of material is subjected to a uniaxial tension. The equations that you see here in blue show the relationship between principal stretches for various cases. For example, the uniaxial tension, where you're stretching the material in one direction, then the principal stretch along that direction has a fixed value, whereas the principal stretches along the other 2 directions are equal in magnitude. And if we assume that it's an incompressible material, that means J, called the volume ratio, is equal to 1. J is actually the product of the principal stretches. So it's lambda 1 times lambda 2 times lambda 3. So if J is equal to 1 and lambda 1 is equal to lambda, then you can easily get what is the value of lambda 2 and lambda 3. Likewise, you can derive these principal stretch values for various different test scenarios. And this is useful because the next step here is to write down the expression for stress for various tests. The expressions for uniaxial test and biaxial tests are shown in the equations here that you see on the slide. The top one is for the uniaxial test, and the bottom one here is for the biaxial test. These expressions that you see here are found by eliminating the hydrostatic pressure P from the expression of stress in the equations for nearly incompressible or compressible hyperelasticity. And then finally setting the volume ratio J to 1 if you are assuming perfect incompressibility. And by that I mean, if we go back to one of our slides back here, this P is the hydrostatic pressure for nearly incompressible or compressible hyperelasticity. So what you do is you eliminate this P based on the conditions for the test. So if you're talking about uniaxial test, then we know that the stresses in the second and the third principal directions are 0. So given this equation, you can eliminate the hydrostatic pressure, and then you come up with this equation for stress in terms of the stretch and the strain energy density and the invariance. Now this stress is the second Piola-Kirchhoff stress, but you can also find the first Piola-Kirchhoff stress and the Cauchy stress. And you can also figure out the invariance as a function of the principal stretches. Same goes for the biaxial tension here, or biaxial tension compression scenario. The goal here is to compare these analytic stress versus stretch expressions for various hyperelastic material models and compare them against experimental data for various tests. The comparison is called curve fitting, which will also provide you material parameters that are required for various hyperelastic materials. So let's take a look at this blog link below that explains a little bit more about finding these stress expressions for various hyperelastic materials. So here I have just the theory that we just discussed in previous slides, and the equations for stress that we just mentioned in the current slide for the uniaxial tension case and the biaxial tension case. Now we have various different types of hyperelastic material models, like I mentioned earlier in COMSOL, Neo-Hookean, Mooney-Rivlin, Aruda-Boyce, and so on. Now, for each of these material models, you have an expression for strain energy density function, which can either be written as a function of these invariants, I1, I2, or so on, or they can sometimes be written as a function of the principal stretches. Whatever be the case, our goal is to derive the stress versus stretch relationship for each of these material models. So you can see here, given the general representation that I showed in the current slide we're discussing, you can figure out the stress versus strain stretch relationship for each of these material models because you know the definition of strain energy density. So you plug that in the equation and you get stress versus stretch. There are two equations listed here, for example, for neohucan, one for uniaxial case, the other for biaxial case. The same goes for Mooney-Rivlin 5 parameters, Aruda-Boyce, Yeo, Ogden. So this is a very useful block that you should definitely look into if you are modeling hyperelastic material and you do want to figure out the material parameters corresponding to the experimental data that you have. Now we have a question here from Mohammed. Can we choose a model based on uniaxial test only? It's a very good question and it often comes up. And the answer to that is ideally no. If you have a choice, if you want to do good, you want to have an accurate model, a stable model, then no, you should not base your analysis or your parameter estimation on a uniaxial test, even though that's all you have or might have. You should look into getting the data for other modes of deformation like biaxial or shear or volumetric compression if there is sufficient amount of compression going on or volumetric change happening in your model. And the reason is that when you do uniaxial tests, you have no information whatsoever of the deformation in other directions, second and third. So how the deformation in those directions coupled with the deformation in the direction you're stretching is really unknown. So in material behavior, in the real world scenario where you're modeling a three-dimensional object subjected to stress strains in all directions, it will not be accurate and sometimes may fail because your material parameters are based on uniaxial test, but the simulation you're doing is not uniaxial. Yes, of course, if the simulation you're doing is primarily uniaxial, then that should be more or less good enough. But usually that's not the case. We have a question here from Matthew. How do we analyze material behavior with different strain rate? So that I will address later on towards the end of this presentation. So right now, I'm really talking about hyperelastic materials where the stress does not depend on the strain rate. Now, to get the material parameters required for hyperelastic material modeling, curve fitting is required against a number of hyperelastic material models. Now, like I mentioned earlier, it is not enough to have just uniaxial data for curve fitting because the uniaxial data does not contain information about deformation in transverse directions. And additionally, when curve fitting experimental measurements, perhaps not all data should be given equal weight. So it may be that the response in a certain strain range has a larger impact on your simulation results. And most of these things related to curve fitting, related to fitting the experimental data that you have for various tests can be done within COMSOL. And here we're seeing an example where I have a raw data on the left-hand side. The green data is for biaxial test, and the blue data is for uniaxial test obtained from real-world experiments where we have the stress versus stretch. What is stretch here? Well, the stretch is just 1 plus the strain. And what we are doing here on the right-hand side is fitting the analytic curves for various different hyperelastic material models to this raw data. So you can see here, we're fitting it to Mooney-Rivlin 2 parameters, which does not look like a real good fit. The red curve here is the fitted uniaxial curve, and the black dotted curve is the fitted biaxial curve, whereas the green and the blue are the raw data. Mooney-Rivlin 5 parameter does a little better. And if we go further, then Aruda-Boyce is good. Yeo is okay. It does not really fit our data so well in this case. For smaller values, it fits the biaxial data well, but for larger values of stretches, it fits the uniaxial data well, so not good overall. But the Ogden material model, as is usually the case, fits both the raw data perfectly, the uniaxial and biaxial both. And this is what you want. You want multiple experimental data to fit against your analytic curves. Okay, so let's take a look at how this is actually done within COMSOL. So here I have an example of, let's say in this case, a uniaxial test where I have stress versus strain. And I would like to fit a hyperelastic material model to this experimental data. So what I'm going to do is open up a already solved example from COMSOL's application library to just give you an idea of how this can be done. And later on, I will then base my demonstration on this kind of parameter fitting, or getting material parameters out of this kind of fitting. So what we have here is this analytic expression that I was showing earlier of stress versus stretch, where lambda here is the stretch. And then you have the optimization interface. It's called the least square fitting, where you import the experimental data. The left-hand column is the stretch, the right-hand column is the stress. And then use the optimization solver here to perform least square fitting, where you declare the unknown material parameters C10 and C01 that are declared here. And then you compute this model. Finally, you will get the unknown parameters. But before that, here's the fitted curve. This blue curve is the fitted curve, and the green dots are the data that you have imported here as interpolation function. So this is a good fit. And based on the fit, we can also extract the material parameters from here of C01 and C10. Now, I do see there are lots of questions here, and I'll try to address them as soon as we get closer to the demo, and soon after the demo as well. So you can see here on the bottom, I can extract the C01, C10, and these are the values that are very important, because these are values I'm going to be, or you will be using in your hyperelastic material model after performing this kind of optimization. So let's take a look at an example here. What I'm going to model here is a hyperelastic foam in COMSOL. And the example that we have here is that of a highly compressible foam compressed by a rigid indenter. The foam is placed on a rigid base plate, and the model itself involves contact modeling between the foam and the rigid objects. Finally, as you can see from the animation, due to the extreme compression, the inner surfaces of the foam also come into self-contact, which is something we'll also need to model. So in all, we need to address contact, and we also need to address the extreme compression of this foam. Now for this model, we will be using the Storaker's hyperelastic material model in COMSOL, which is used for modeling compression of foam and also models volumetric changes. And in the model that I have here, I already have the material parameters, which you would ideally find from curve fitting without assuming any incompressibility. Here I have some representative material parameters that I will be using. So let's take a look at how this will be modeled in COMSOL. So I'm going to start with COMSOL GUI here. Some of you are already familiar with the COMSOL GUI. Some of you might not be familiar with the COMSOL GUI. Now the next step here to choose 3D, 2D, or 1D modeling. So I'm going to select 3D, and we'll select solid mechanics as our physics, which is what we're going to solve for, three-dimensional solid. So I will add that as a physics, and then move on to a stationary analysis or steady state analysis. Now the next step here is to bring in your geometry. I don't want to draw my geometry, so I will borrow my geometry from a file where I already have the geometry drawn. It's a quarter of the three-dimensional geometry. I haven't drawn the full spherical shell, so it's ideally a full spherical shell between an indenter and a cylindrical base plate at the bottom, but I'm just drawn here a quarter of the geometry instead of the full three-dimensional geometry. And I will also import some parameters required for the hyperelastic material model. I've already populated here in this text file, which has some parameters called mu1, alpha1, mu2, alpha2, beta1, beta2, and we'll see shortly where these will be used. I'm going to compress this by a total of around 10 millimeters, and the we'll see what happens at that point in time. The next step here is to define the contact between the hyperelastic material and these indenters. So I'll define them as contact pairs. And COMSOL, what you have to do is declare a source boundary corresponding to the contact pair and a destination boundary corresponding to the contact pair. And there are some rules regarding source and destination. One of them is that the source should be rigid and the destination should be soft. We'll have another such pair for the bottom. So this is the source and that becomes the destination. So we have that. Then we'll do another third contact pair, which we need to include in case there is self-contact between the upper and lower parts of this foam. So I'll select one part of this foam as source and the bottom part as destination. This will take care of self-contact whenever that happens. Now, for those who are new to COMSOL, I've never seen COMSOL. This is the COMSOL GUI, and this is the model builder here on the left-hand side. This is where you do all the modeling steps, and you usually go from top to bottom like I was going. Define parameters, declare your geometry, define some variables, define the physics, define the material properties, mesh, solve, and post-process. And whatever you do, it will have a settings window here in the middle, and on the right-hand side, you have the graphics window for visual feedback. So let's go here to the materials branch. I'm going to add my rigid material here, and let's say this is made of structural steel, the top and the bottom indenters. So I will only select the top and the bottom as structural steel. And I'll go to the physics interface, which is solid mechanics. And by default, what we have here is linear elasticity, which is not what we want. So I will include a nonlinear or hyperelastic material model by right-clicking on the solid mechanics interface. If you right-click on the solid mechanics interface, you'll see certain conditions here, which are volumetric conditions, and you'll see several boundary conditions at the bottom. If you're looking into material models, then you'll choose one of these, so hyperelastic. Choose hyperelastic and declare the rubber foam, or sorry, the spherical foam as hyperelastic material. And then this is the place where you will choose what type of material model you want to use. So let's say we have decided we are going to use this storakers based on our curve fitting that we may have done prior to this. And once you do this, then COMSOL will ask you for parameters. And this is where you put in the parameters that you get from curve fitting. So let's see here, we're going to put in the parameters that we already have imported in our text file or parameters section that we have defined earlier. And I'm going to put this data in here for parameters, mu2, alpha2. So where do these parameters really go? Well, these parameters are used to define the strain energy density function, which is a function of this shear modulus, the alpha parameters, and beta parameters you can see here. And also, of course, a function of principal stretches and volume ratio, which determines how much compression is happening in your material. So that's where it goes, these parameters. That's why you need them. The next step here is to assign the contact boundary condition. So this will do through these contact pairs. So we have contact pair 1 and contact pair 2. That takes care of the contact between the indenter and the hyperelastic material. And then again, another contact pair for the self-contact. That's contact pair 3. And finally, now we need to put in the constraints. One of the constraints is that the bottom is fixed. So I'm going to select fixed constraint and fix the bottom. And the top indenter is moving down. So I'm going to prescribe a displacement for the top indenter. So use this prescribed displacement for the top indenter. Now it's only moving down. That means not moving in the X direction, not moving in the Y direction. It's only moving in the Z direction. And here I'll type in the Z direction displacement, which is 10 millimeters, for which the parameter name is disp_max. So minus 10 millimeters multiplied by a user-defined parameter para. This para is initially 0. So we'll change that value as we compute this study. And we also need the symmetry boundary condition because we are only modeling 1/4 of our geometry and not the entire geometry. So I'm going to select these symmetry boundary conditions here. Now what about the mesh? Now this is a very important criteria here, the meshing. You could go with the default tetrahedral mesh here, but that's not the one you would ideally want if you're going to compress something too much. So if you're going to compress something too much, you better have an isotropic mesh, which is usually created by using structured mesh. So in this case, to create a structured mesh, or let's say brick type elements or hexahedral elements, what I'll do is first create a two-dimensional rectangular mesh on this, on the cross-sectional boundary of this hyperelastic material. And by doing this, I'll also have explicit control over the number of elements. So let's say I want 3 elements across the thickness of the spherical shell, and about 20 elements on these circular arcs of this spherical shell, 10 each. So that builds a 2D. That will build a 2D mesh on that boundary, and we'll sweep this mesh for the rubber shell by telling COMSOL the sweeping direction. So this is the source, and this is these are the destination boundaries. That means COMSOL will sweep from source to destination. And let's say 10 elements between the source and destination. So that's that. And now we will use another swept mesh, and in this case, assign the source and the destination, or the direction of sweeping, for this spherical indenter there, and leave it to, this is now a quite coarse mesh. We should ideally use a finer mesh, but just for this demonstration, I'm keeping the mesh coarse there. Ideally, you would put another size to it to refine the mesh for those elements, those geometries as well. Now, the last few steps basically involve, excuse me, changing the parameter values. So this we can change in the settings of the step 1 stationary step. Here we can click on something called as auxiliary sweep. And this allows us to change the value of the parameter from 0 to 1. So I'm here sweeping from 0.025 to 1. So as the parameter goes from a small value to 1, my displacement will become from small to exactly 10 millimeters. And let's say I'm going to do plot while solving. So I'll enable this, and we will just, now if everything is set up here, well, we just need to compute the model and see what happens here. So while it is computing, let's address some of the questions here. Is PDMS considered a hyperelastic material? Yes, it can be. Certainly can be. Could COMSOL model the buckling behavior of hyperelastic material under compression? Yes, definitely. COMSOL can be used to model buckling behavior of hyperelastic material. And after this finishes, I will point you towards one such example model. Now we have a question here from Rafid. Is tension model using the same models for hyperelastic materials? Yes, you can model tension using, I'm not sure I understand the question was same models for hyperelastic materials. Yes, you can use any of the material models inbuilt within COMSOL for tension, just uniaxial tension if you'd like to. Now, Chenshen has a question here. What is self-contact? Can we build the hyperelastic ball as a whole? Yes, of course, you can build a hyperelastic ball as a whole. It just will take you a little more time than building 1/4 of it. You get away with 1/4 because it's symmetrical. What is self-contact? Self-contact here basically means the inner surfaces of the ball come into contact with each other. And that's what we're trying to model. So now you see the computation has begun, and this is compressing right now. And this takes a few minutes. So I'm not going to solve the whole thing here right now. Otherwise, we'll be staring at our desktop silently for a few minutes. So I'm going to open up a solved model here, the same model that I've solved, and we can take a look at the results here. So what we are seeing here is the displacement plotted for a sector of the geometry where I have taken out one part of the geometry. So I've created a data set that allows you to plot on this geometry here, where I have removed one sector of my full geometry. Right? I've taken 3/4 of my entire geometry. That's what I'm showing just for clarity's sake. And you can see here, finally, at the last parameter value, the foam has compressed entirely, and we could probably animate this. So let's animate this with a player. and see how this compression proceeds. And what we're looking at is the net or total displacement. I should zoom out. So let me zoom out here a little bit so that you can see the full analysis here. Okay. Like that. So of course it comes into self-contact there at the end. We can also plot the stresses as a result of this compression, and we can animate those as well. And since we are modeling contact, we should also be able to compute contact pressure everywhere between the indenter and the spherical shell, and also between the surfaces, inner surfaces of the hyperelastic shell. So that that is the von Mises stress. And we can also plot the contact pressure easily. And let's see here. So what you're looking at is initially when there is no self-contact, you basically have the contact pressure between the spherical shell and the indenters. That's why you see only two colored regions for two contact surfaces. But as soon as you have self-contact at the end, then you will see, then you should see three such surfaces, colored surfaces right there. One at the top, one at the bottom, and one for the inner surface of the spherical shell. And you can compute the contact pressure there. All right, now going back to my presentation here, you can also use user-defined hyperelasticity, meaning you don't have to, if you have a material model which is not inbuilt into COMSOL, you can write the strain energy density in terms of inbuilt variables. So we have inbuilt variables for principal stretches, invariance, and so on. And in fact, the same model I also have here, I have already declared a strain energy density function user-defined, which is a function of the principal stretches that I have written out here as a variable. And I could have just gone here and chosen user-defined, and this one then here is computed from my variable there. Now, multiphysics interactions such as thermal expansion, plasticity, hygroscopic swelling can also be incorporated in hyperelastic material model. And these effects, including the external strain or initial strain of a hyperelastic material model, can also be included, as is shown in these equations here. And this is done by removing the inelastic deformation from the total deformation. So F here is the total deformation. FIN is the inelastic deformation corresponding to thermal expansion or hygroscopic swelling or plasticity or external strain. And FEL is the elastic deformation gradient. So you calculate FEL based on the total deformation gradient times the inverse of the inelastic deformation gradient. So all of these can be incorporated. Now, earlier we had a question about modeling materials which are strain rate dependent. Now these are called large strain viscoelasticity model. In the beginning of the presentation, I stated that we use purely hyperelastic material models for scenarios where stress does not depend on strain rate. But for materials which exhibit rate-dependent behavior, a large strain viscoelasticity formulation can be used. The large strain viscoelasticity formulation is an extension to hyperelasticity and basically includes the viscoelastic material models such as the generalized Maxwell model, standard linear solid model, Kelvin-Voigt model. You can also incorporate temperature effects via the inbuilt or user-defined time shift functions. So this you can easily do by going here, right-clicking on it and choosing viscoelasticity, and then choose a material model. Generalized Maxwell is the most accurate one. Choose a model for the temperature effect. And that's the way to model large strain rate dependent materials, which are both hyperelastic and viscoelastic. Now, let me address a few of the questions here that we have. We have quite a lot, so I may not be able to address all of them. But let's see here. Now, James has a question here. How would one overlay thermal effects in these models? Yeah, good question. COMSOL is perfectly suited for this. What you would do is right-click here, choose Add Physics, choose Heat Transfer in Solids, and you would add the heat transfer interface to your model. And since you have contact between two objects, you need to declare thermal contact there. So you would go here, pairs, and choose pair thermal contact, and define it on the contact pairs like that. you cannot have perfect continuity of temperature because it's a contact, it's not a union material. So that's how, and then you could go ahead with any heat transfer related heat source or heat dissipation or cooling that where you want to model. All of that can be included here. And when you want to model thermal expansion, you right click on hyperelastic material model and choose thermal expansion. So that's how you would model all of it. All right, we have lots of questions here, so we can take a few more questions. Let me see what the short ones that I could address right away. Now we have a question here from Tom. Contact is no slip here. Is it possible to include interface slip? Yes, it is possible to include interface slip here. If you right click on contact, include friction, that's what you would probably need to have some kind of constraint on slipping. And the contact here that you have allows the material to slip if you let the material to slip. But if the material slips, what is going to stop it from moving infinitely in a particular direction? Well, in real world scenario, you would have frictional force. So that's what you would add as a friction force here. Okay, so we have a question here from Abhishek. Does COMSOL model viscoelastic materials? What material characterization data is needed for such a material? Yes, like I mentioned earlier, it does. What material data you would need, that you would depend on which one of these you're going to use. So if you're using generalized Maxwell model, then it is the most accurate ones, and usually you represent the material with a series of springs and dashpots. So what you need are the shear modulus of those springs and the viscosity of the dashpots. And again, to get those things, you need to do a curve fitting of your real world material, which would be in the form of either the Young's modulus versus time or shear modulus versus time. When you do the curve fitting, you can get the unknown parameters of the Prony series that usually is required to feed it into this kind of material model. Is there a way, Nolan has a question, is there a way to see the amount of surface area in contact with one another? Yes, of course, that is also something you can do. Let me get rid of all of these things that I've added. But what you would ideally do here is you would right click on integration, surface area, and you can perform integration on COMSOL or on any area and conditional integrations where you say, hey, integrate number 1 if the contact pressure is really greater than 1. But let's put in some little bit higher value than 1 to avoid some numerical issues there. Or you can also put 1, for that matter. But if you evaluate that, then you can see, you know, as the parameter values are increasing, my contact area there is increasing, and I can plot it as well, like here. And that's how you would compute the contact area. Okay, let's see. We have lots of interesting questions here. Now we have a question here. Can I assume any anisotropic properties? A question from James. Can I assume anisotropic properties that handles through the CG equations? I'm not sure what the CG equations mean there, but anisotropic properties, yes, you could assume anisotropic properties as well. But in those cases, you will have to resort to user-defined material model. And we do have an example here for anisotropic hyperelasticity, and this is the one you would want to see. It's called the arterial wall mechanics, where we use a specific anisotropic hyperelastic material model. And I can quickly open this one, where you're basically modeling soft tissues in arterial walls, and to represent the strain energy density function, you have to take into account anisotropy, and all of that is defined as a predefined variable, meaning you define these variables that represent the strain energy density function. And then the strain energy density function can be used in the user-defined hyperelasticity material model. And while that opens, let me see a few other questions. One more question here. Can you add in vibration from an acoustic source? Yes. So that's a question from Douglas. Yes, you can model vibration from a acoustic source easily. That was something we would call acoustic structure interaction. In fact, in some of these microphone models where the membranes could be hyperelastic, you may need to account for hyperelasticity. So definitely, and that would be part of the acoustics module in COMSOL, where there's a specific interface called acoustic structure interaction that will allow you to model hyperelastic materials along with acoustics. So here we have this anisotropic material model where we have a user-defined expression for strain energy density, and you will see here we're accounting for these fiber directions in this hyperelastic material. And these fiber directions are defined by certain parameters, and you put in these variables that represent the strain energy density. So modeling this kind of anisotropy, of course, does require a little bit of work, but once you have the material model that you want to represent or model, it is pretty straightforward here. We're running short of time, so with this, I want to thank you all for this presentation. I want to end this presentation. There are, of course, lots of questions here that I would like to address, but we will address them later on, if possible, via support. Thank you all for attending.